So our next speaker will be Babak Kalantari from the Paul Scherrer Institute. Babak is a group leader for embedded software and has long-term experience in accelerator timing and related applications, specifically with the Micro Research Finland event system. Babak will be speaking on the SwissFEL timing system first operational experience.
Thanks for introduction. Hello, everybody. So I'm going to talk in the next few minutes about SwissFEL timing system, but I will not talk about the performance of the timing system components, but more focus on operational aspect of the timing system and maintenance and also timing related applications. So I give you first an introduction, very short introduction to the SwissFEL facility. It's an FEL facility under construction and being commissioned actually partly in Switzerland at Paul Scherrer Institute. And the timing system is supposed to provide precise triggering across the whole facility, including beamline and experimental stations. It is supposed to do the rep rate and beam rate controls. It should distribute operational critical parameters of the machine, and it should assist machine or beam synchronous data acquisition and controls, and it should support also machine protection system. Here you see an architecture of our timing system. On the left you see the master timing system, where the generated timing signals are fed to the first layer of distribution, and then they go through fiber optic links, single mode, to each subsection of the machine. And then in each subsection of the machines, and also in beamlines and experimental stations, we have local distribution systems, which then, of course, as I said, the single mode fiber arrives at the local distribution, and then we go with multi-mode fibers to the next level of distribution, and finally we end to event receivers. And just to add, the rep rate of the SwissFEL is 100 Hertz, the nominal rep rate, and the event system clock is 142.8 megahertz given by master oscillator of the machine, and we use active delay compensation. We manage several form factors in SwissFEL. Our mainstream is VME and PCI Express. PCI Express we use, form factor we use mainly for motion control and for camera systems, but also we have been dealing with embedded EVRs, and they are increasing over time. And as you see here, and you can compare the numbers to the last year, but as of now we have about 70 event master in the network, in the timing network, more than 140 VME EVR, more than 40 PCI Express EVR, and more than 150 embedded EVR. And since the embedded EVRs are implemented on different chips and different groups, non-standard interface is a challenge that we have to manage. And also I would like here, in the spirit of today's keynote talk, ask Micro Research to provide the open IP for the MRF, and I'm sure that he will get even more customers. Okay, so now I would like to talk a little bit about the beam rate control. In general, the event rate is a challenge in the pulsed machines. Since every system and everybody wants to have his own event, he would like to have flexible control over the event rate, and also kind of independent but yet synchronous with the machine and beam. So this is in general a challenge, but I don't address this in this talk. You can read it in the paper. What I will focus now is the method of the beam rate control that we do in SwissFEL. So since systems would like to stay in their operating point, or so to say, they would like to be warm and to be able to provide a stable beam, because if you stop triggering, they might not be able to produce exactly the same beam as the previous pulse. So the technique is that not to stop the trigger. So basically you triggered, for example, an RF system at every pulse, no matter if you have beam or not. But if you look at this side, on the green side on the left, we have pulse with beam. So we have RF event, and slightly after that, subsystems have triggers on their system, and here we generate beam. On the next pulse, we do not want to generate beam, but we send still the trigger or the event to the systems, but they generate the trigger a little bit later, typically a few microseconds, and this is then arriving at a different phase to the RF system, which then does not accelerate the beam, and basically stops the beam. So this is the principle that we use in all machine timing mode to basically control the beam rate. And this can be controlled by software when the user wants to change the beam rate, or it can be controlled by hardware, which can be an input from the machine protection system, which needs to instantly reduce the beam rate or even stop it. In practice, this will become more complex because we use the same system, as I mentioned. Also, we use the same mechanism to apply the rate control to the laser system, for example, and we have only beams in those pulses where laser and RF system are on beam. And of course, based on that, we have to calculate the actual beam rate and distribute the beam status to all systems. Another issue that we faced during the commissioning was the issue we had with the super period. So super period is supposed to synchronize the events with a majority of subharmonics of the reference clock, which is used in different systems. But if you have unrelated clock in some subsystems, which we have in SwissFEL, in some low-level RF systems, when you restart the timing system upon power up, or if you want to update the system with the software and you restart the system, since the super period is generated internally, it doesn't know about, so the relative phase with respect to unrelated clocks cannot be maintained. And what happens is that, for example, assume that I reboot the system and now look at here. So there are different possibilities for the event trigger with the phase of this unrelated clock. And this is a problem when we restart the system, and then the low-level RF guys have to sit and do a cumbersome procedure to tune the machine with respect to the new phase of the event triggers. So the solution we came up together with low-level RF guys was to generate a super period on an uninterruptible system on UPS directly from the master oscillator and feed this to the event system. And event system also provided the possibility to measure the phase of this external super period, and even to select at which phase we want to start playing the sequencer of the events. And this works nicely, so when we reboot the system, if this system stays uninterrupted, they don't need to readjust anything, and we can exactly reproduce the relative phase of the event with respect to the external super period, which does not change. Okay, now I would like to talk a little bit about little bit less interesting stuff. So the most interesting stuff are normally when you design your system and then you put everything together and implement it and everything works. But this is not the whole story. Then you have, in case of SwissFEL, a large network to maintain. So, and if you're an experienced engineer, you know how good cook we are in making spaghetti cables. And this is what you see. Now you say, okay, I make it nicer, I do nice labels, and then my problem is solved. But I would say not. So the problem is here, if you're called in the middle of the night and you want to fix a problem, or you swap the cables and then just you forget to label them correctly, then you don't know what is connected to where. And when you want to do the troubleshooting, when an event receiver fails or a component fails, you want to know exactly the path between every event receiver up to the master. So what we did is that we introduced the topology ID, which is based on a simple principle. So each component maintains a topology ID. Each parent sends the topology ID plus the port number to the next component which is connected to it. And based on that, we developed an application. So we know the device names from our inventory database, and we know the topology ID when we can dynamically build the tree, and we can even save the previous topology and see if anything has been changed in between. And even we can, by clicking on this tree, we can get to the components and diagnose the component with the parameters. Now, the last applications that we are busy with currently under development is what we call a complex triggering application. At some beamlines, we have, like Aramis beamline, we have more than one experimental station. At each experimental station, there are experiment planned which require a rather complex triggering pattern. So basically a trigger and acquisition pattern. Typically one of these experiments is pump probe experiments, where you pump and sample with a laser, and then you want to probe it with FEL pulse. And this requires a complex definition of triggering sequence and then an acquisition which is related to that. And since this experimental station want to do this experiment independently at the same time sometimes, and we have also the architecture that I have shown you at the beginning. So each experiment has its own branch of distribution, and such a complex triggering pattern has to be managed. Then we thought we had the idea to implement this triggering application in a sub-branch of the timing system. So to implement it here, not on the top master, in order to avoid a higher complexity to the master. And also this provides us with a shared event code space that can be used by both beamlines. And we can even start this complex triggering pattern with a global event, or upon occurrence of a certain pulse ID or a press button. And we can even do synchronized experiment at both beamlines if it is required. And this gives flexibility also to usage of the timing system. So, and at the end, I would like to thank all members of the controls group, and also the discussions and ideas that we developed together with the other expert groups, low-level RF diagnostic, lasers, and also collaboration that we had also with Micro Research Finland, the ideas that Micro Research implemented nicely for us, and also COSILAB for their contribution. Thanks.
So I think we have time for one question. Okay, we got two over there.
So moving around your global events in case of interlocks, are you not afraid that one day you will hit on something?
With global events?
So in case of interlocks, you shown that sometimes instead of not sending the global event at all, you just move it around a bit.
Yes.
So first of all, why do you do that? And then, are you not afraid of, just by coincidence, hitting on something important?
No, we send the events. We do not stop sending events. We send the events at every pulse. Yeah. But at each pulse that we do not want to generate beam due to any reasons, then we send an additional event which tells to the system, now you switch to a different delay.
Okay.